students. Today we will study GRU. GRU stands for Gated Recurrent Units. We learned about we have learned about our CNN in the beginning, followed by RNN, then LSTM. Now we'll look at GRU. In the upcoming session, we will look at Bi-LSTM, means bi-directional LSTM, and bi-directional bi-RN. These are the architectures of deep learning, various types of architectures. If you recall, our CNN is convolutional neural networks for images, RNN recurrent neural network mainly for text and time series data. LSTM long short term memory. This is an extension to RNN, or we can say variant of RNN, a newer model that overcomes the problems that are faced in RNN, which is vanishing gradient problem. And we looked at how we have forget gate, memory gate, and various other options in LSTM. Moving ahead, today we will look at GRU. GRU is a variation of LSTM. And how does GRU works? You can call GRU as an improved version of standard recurrent neural networks (RNN). And how is GRU different from RNN or LSTM? RNN suffers with the problem of vanishing gradient. As the learning process moves ahead and as this data moves forward from left to right direction, the gradients which are generated from this back propagation and weights are updated, and in that process uh, the weights become so low that they do not contribute in the learning process in uh, further cycles of training. That is the problem of vanishing gradient descent in standard RNN. GRU, what it does is it uses two kinds of gates. They are update gate and reset gate. And these two decides which information is to be retained and which information is to be eliminated. All right. And then here this update gate and reset gate are basically two vectors that decide what information should be passed to the output. Let me give you an analogy. You have friends, okay? You have your school friends, you have your college friends, you have your university friends, and then you get some information from your school friend. Let us say if your friend one, okay, from school means SC1, SF1, send you some information, and SF2 also send you some more information. Like that, you get messages and information from many sources. Now it is up to you. Some of the information you may receive from college friend, from university friend as well. Whatever information you are receiving, it is up to you what information is to be forwarded to the other groups. You feel that some information is not at all important, not relevant, so you can just delete those messages and do not forward them. And there are some important messages or information updates that you need to share with your other group friends, because you might have received that information from here and you would like to pass on to this side and this side. That decision, how much information and what information to be retained and passed on to the output, and what is to be discarded, that is done in GRU. And this is not performed in standard RNN. Standard RNN does not have this um, uh, method of choosing the data that is to be passed on and eliminating the other data. All right, do you understand the difference between RNN and GRU? And how does GRU achieves this? Which how do you do? Because humans have got brains and then they they can take decisions, they have information knowledge and about the current situation in the world or in the professional world, in academic community, like that. You may based on these many factors, you may decide whether to forward or to drop. GRU does that by using gates: update gate, reset gate. These are the units or the nodes. This recurrent neural network with gated recurrent unit. If you just recall, recurrent neural network, it had some nodes, the units, and those units did not have these type of information, these type of gates. This type of architecture and structure was not there in normal recurrent neural network. Let me open and show you. This is LSTM. Look at this LSTM. LSTM had all this one. These are the units in LSTM which had forget gate and input gate and output gate. And it has got this is forget gate, this is input gate layer, this this one is output layer. In LSTM you had four different gates: forget gate, input gate, and output gate. And this one, the one that goes along this horizontal line here, represents the state, cell state. This is the cell state. This cell state, C at time t minus 1 and C at time t. All right. So this is the previous state. This is the present state. How it is computed? It obtains the previous state and it is getting the input from here, and it is getting the information from the previous cell. This is also previous cell state. This is also previous cell output. So that it is taking, and then it is performing sigmoid operation, tanh operation, and multiplication operation, and sum operation, and then deciding on which information to be retained, which information to forget. Here, this is the input vector. This is the uh, vector that decides what information, contextual information, what information to be written. Whatever information you want to pass on, there you will find ones. The information which you would like to forget, there you will have zeros. If you have if you multiply zero with any number, the output will be zero. If you multiply any number with one, the output will be that any number. So in this scenario, if you observe here, you have 6214, but you are passing just 62, not 14, because 14 you are just forgetting, removing from the vector. That is what is happening in LSTM and GRU. If you look at recurrent neural network structure is like this. It had input, it had output, it had hidden layers, and then these hidden layers share the weight, and then there is a weight between input and hidden layer, and there is a weight between hidden layer and output. So I hope that this all made sense to you. Now we are looking at GRE. We saw RNN. RNN are nothing but simple units like this. We saw LSTM. It is very complicated structure. It has got state, it has got forget logic, input logic, output logic, and output will go out and state also will be sent out. Going ahead to this recurrent, gated recurrent unit, eh, here you have the output information from the previous unit. Consider that this is the current unit. It receives output from previous unit on this one, and it forwards its output to the subsequent unit. This is at time t xt input. This x sub t minus 1 is the input at the previous time. X sub t plus 1 is the input uh, at future time. And the output you can give out the output, or you can just give one single output. There is an option we already studied in RNN. You can give output at every layer, or you can combine this processing and releases only single output. These are all different types of RNN. You had one to one, one to many, many to one, many to many. Here it can be this input, output, and forwarding the output to the subsequent layer as well. What is happening here that we will look at in detail. This is from previous unit output, ht minus 1, ht, the output of this present unit, and this input is feeded, and some operation is performed between input and previous units output. Use something. And then this is sigmoid operation. You perform sigmoid operation. If you observe here, xt, that input at time t, x is the input at time t, is traveling along this line and also branches out to different directions. Look at here, there is one traveling on this line, another on this one, and one is is summed up with the previous output. Further, this summed output of input and previous units output is given to the sigmoid function. The sigmoid function gives the result. Here you see the result is going at two different places. Uh, no, it is going only to one place. Here ZT is traveling, and here it is coming to this point. Uh, this output from previous unit is also going on to multiple gates. One is here, one is here, and another one is here. And what how this is carried out, we will look at. This is plus operation. Plus is plus operation. This sigmoid function, sigma. This is known as Hadamard product, and tan h. Tan h is a activation function. Tan h function, hyperbolic tangent function. First, coming to this update gate, for time step t, how update is calculated is in this manner: W z, W super z, and xt into xt. What is this W? W is the weight. Weight into this input value. mm, Sum with, this is also the weight. Uh, Weight into the previous unit output. ZT. This one, ZT. How are you getting ZT? You are getting ZT by performing this sigmoid operation on this x t into w. Means there is a weight, right, associated, and h also there is a weight associated. With ht minus 1 also there is a weight. With xt also there is a weight. Every connection there is a weight in neural network. That you perform sum operation and then takes the sigmoid value. And that sigmoid value will give the any value between 0 and 1. This is known as squash the result between 0 and 1. In this scheme, this is the scheme for this update operation. Here it is capital W, here it is capital U. And what is the use of update gate? Update gate helps the model to determine how much of the past information from previous time steps needs to be passed along to the future. This is past information. How much of it needs to be passed uh, to the future? Please remember this point. Reset gate. Reset gate is used to decide how much of the past information to forget. Update is to remember how much of the information is to be forwarded to the future. And reset is how much of the past information to forget. And that is obtained by this WXT sub t minus 1 and again a sigmoid activation function at this point. So what is here that this is update gate, this one is reset gate. From update gate you are getting at ZT, Z sub t here, that is that information that has to be passed forward. And here this one RT is the information that need to be eliminated. And then from this it is determined what information memory contains in the present unit. And how is that calculated? That is calculated from this weight into xt again input weight plus some operation. RT is that reset output of reset gate. This hammered product is element wise product. Element wise product is if you have like this, what you do is you perform multiplication of the corresponding elements. This is at position 1, 2, and 3. What are the elements at position 1? This 1 and 1. So you perform multiplication, which gives 1. Here you have position number 2, you have 2 and 0, which gives 0. At third one, you have 3 and 1, which gives 3. So this is known as a Hadamard or element-wise product. Okay. So element-wise product you perform means from here you will know what need to be reset. Reset is like what you're discarding, which information you're discarding. That you multiply with this one and add with this input and take tanh value, you will get the current memory content HT. HT is the current unit's state or the contents. So how it is calculated? It is calculated as multiply the input xt with the weight w and h sub t1 with the weight u. All right. Uh, this part and this part. Then step 2 is calculate the element-wise product between the reset gate RT and UH sub T1. This is reset gate RT element-wise product or Hadamard product with this part. That will determine what to remove from the previous time steps. An example is given here. Let's say we have a sentiment analysis problem for determining one's opinion about a book from a review. He wrote, "This is a fantasy book which illustrates." And after a couple paragraph ends with, "I did not quite enjoy the book because I think it captures too many details." This is a review. And to determine the overall level of satisfaction from the book, what we need to remember, what is important in this, the review may span across 10 lines. Okay, RNN, GRU, LSTM mostly they work with uh, text data. So this is the text data. What is the overall sentiment of this paragraph, whether it is positive or negative? Which line will give the overall picture that I did not quite enjoy the book? This line says that it's rather a negative feedback. Although there are some positive lines, however, it concludes with a negative remark. So to determine the overall level of satisfaction, we have to remember this last part. Even if we forget this, all the previous lines, it does not matter. So here, essentially, you can reset this, the previous lines, and this last line you can retain. So the neural network approach to the end of the text, it will assign RT vector close to 0 to all, washing out the past and focusing only on the last line. When the GRU reaches this point, it just resets the entire information and preserves only this last part. Sum up the results of step 1 and 2. We see here it's summing this operation. Apply the nonlinear activation function tan h. Then we are applying this tan h. To obtain the current memory content, this is what has been done in order to maintain only that information which is required. This is that part. RT from reset gate, element wise multiplication of the previous output, sum with xt and w, and then take the tan h, uh, perform tan h operation on that to obtain uh, ht dash. Then there is a final memory at the current time step. What is happening in the final memory at the current time step? The steps are given here. Apply element-wise multiplication to the update gate ZT and HT1. ZT element-wise multiplication with HT minus 1. This HT minus 1 you are getting from the previous unit. ZT you are calculating with the current input and previous unit uh, by applying the sigmoid function. That is ZT. That ZT uh, perform element-wise multiplication with HT minus 1. Here 1 minus ZT. Whatever is ZT, if you subtract 1 minus ZT, then you get the other part. If the if total information is 10110, if I say ZT is this 10, then if you say 1 minus this, it will be this part. Element wise product with HT a dash. HT dash is what has been obtained here. In the previous step, here at this point, HT dash was obtained. That you perform element wise multiplication with 1 minus ZT. Perform then later perform the sum operation to get HT. HT is the uh, final state of the present unit. This one. You are getting here HT dash and this. When you perform sum, you get HT. It looks a bit complicated, but then if you just go through it once, and then it becomes easy. Once try to understand here, from here only, this HT minus 1, T denotes time, HT minus 1 denotes output of the previous unit, HT is the output of the present unit, and here you have update, here you have reset, here you have HT dash, and here you are getting HT. In between, you are performing sigmoid operation, you are performing sum operation, element wise multiplication denoted in this manner, and there is a dot and a small circle. Uh, this one is also known as head diameter product. Tan H sigmoid activation function output is between 0 and 1. Tan H output is between minus 1 and 1. These are the operations, and every uh, connection between xt and other units or uh, gates will have weights associated w, and this ht minus 1, when it is connected with the other gates, will have a weight of u. U and w are the weights. If you remember this, and then if you remember the equations for ZT, how is ZT computed, how is RT computed, how is HT dash computed, and how is HT computed, it's sufficient to write about GRU and understand about GRU, gated recurrent unit. Okay, now we will look at bidirectional LSTM. Any doubts in this GRU? Bi-LSTM. Bi-LSTM is bidirectional LSTM. These are the articles uh, you can find on Medium blog. Medium is a very good blog where you find articles on various topics, and especially this deep learning and all the other architectures in deep learning are very well defined in that blog. I urge you all to uh, go through Medium blog and create a account. You can also write your own blogs, articles in that blog. If you recall, this is a neural network: input layer, hidden layer, output layer, and every connection is having a weight, and every node has two operations: sum operation and uh, activation function. Output layer, you can have sigmoid activation for two class problem, and you have a softmax output activation for uh, n class problem, more than two class. You have to use softmax. These are the activation functions at the output node. RNN, recurrent neural network, will mostly work with the text data, and here you have got inputs, and this architecture represents many to many, where you can have outputs, and also because it is self connected, this activation or A, the block A is connected to itself. And students, please remember that you may not find a standard nomenclature and standard terminology. I referred H for hidden unit and Y for output, but in this article you can see that H is like an output which is given out of this, and A is basically about this activation. It is self connected. So when you expand it, when you expand this for values between 1 and n, or 1 and t, here t, because it is all about time, previous time, present time, and next time. Then you get this kind of architecture for rn. And working of rn converts independent activations into dependent activations by providing same weights and biases to all the layers. It has got same weights, and it reduces the complexity of increasing parameters because weights are shared, whereas in CNN weights are not shared. Every node has a separate weight to the every other node to which it is connected. And memorizing a function which RNN performs. A CNN does not remember anything, does not memorize, whereas RNN memorizes. Memorizes means, suppose if I tell you that RNN is a recurrent neural network and LSTM is long short term memory. If if it is given to CNN, CNN forgets what I told before LSTM. Before LSTM, I said about RNN, but it forgets previous data. It just remembers current data. Next, if I say GRU, it forgets previous two and remembers only GRU. That is CNN. Whereas in RNN, it remembers even the previous data. If RNN is set followed by LSTM, then LSTM, when the system is at this uh, time, at this data point, it even remembers its previous input, which is RNN. Further, when it goes to GRU, it is at this xt. At time t, GRU is there. At time t minus 1, LSTM is there. At time t minus 2, RNN is there, and all are remembered in RNN. That is possible because of having same weights and then sharing of the weights and biases. Therefore, these three layers can be joined together such that the weights and bias of all hidden layers is the same into a single recurrent layer. You can say this is a single recurrent layer. If I say here W and U and V, then you will get same W, 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 and here same U, 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 and same V, 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 V. Going forward to Bi-LSTM, bi-directional long short term memory, and how that this name has been given to this type of network, which is known as long short term memory, because this network can remember few data elements in the long run, means long memory, and few only in the short memory. Like we had seen forget gate. Forget gate means it is like remembering something for a shorter time. If something is forwarded to the next unit, it is like remembering it perhaps for longer time. And the same thing if you forward further to the next unit and so on, then it is remembered for more time. That is Bi-LSTM. That is LSTM. Bi-LSTM is, we know that the input travels from this left to right in the forward pass. And during learning, that gradients are obtained, and then uh, weights are updated. However, input part passes from um, left to right in only a single direction. When it is said that it is bidirectional, then the input is given from the left as well as from the right. For instance, if I give you an example of, okay, here example is given. A unidirectional LSTM will look only from this left direction. The boys went to, and this LSTM, unidirectional LSTM, does not have any idea what is there in the input beyond this two, because it is reading one after the other words. Whereas in bidirectional LSTM, what you do is you feed like this and this. From here, if you feed the boys went to, from here they might be getting like this pool, the, of, out, got, the, then, and. So here you are getting the right part of the sentence. Perhaps here you are getting the left part of the sentence. Actually, it is, the entire sentence is feeded in both direction, forward and backward direction. Then that kind of LSTM is known as bidirectional LSTM. What is the use of bidirectional LSTM? Sometimes there are some words uh, whose context can be decided based on the neighboring words. When you try to find something on Google, if you say that colleges, okay, college, if you type colleges, it start giving some queries which adds the second word, third word, and so on. So if you just type colleges, then here you get suggestions from the Google. Colleges near me, colleges offering MCA, colleges of having A plus grade, colleges uh, offering a dual degree, dual degree program. Several suggestions will be given. If um, a word is given, this word colleges, then what is the true meaning of the entire sentence? It depends on the other words as well, not only on this word. You have colleges near me will give a meaning to this sentence, or to a phrase. to this phrase, you get a meaning, and then Google will come up with the results. If you don't know what is there after colleges, means the system, the LSTM. If LSTM does not know what follows this one, then LSTM may not be able to predict what may come as the succeeding word which are more appropriate. Suppose if you say colleges from one end, forward LSTM, and me from backward LSTM, then immediately this LSTM can come up with a word near, because from these two words it has derived a context and has uh, you know, come up with the more appropriate word which is near fitting in this context. So that is the advantage of having Bi-LSTM. Oh, here it is. Let us try to open this again. This is Bi-LSTM. Figures have not are not saved properly. Actually, I saved this. This RNN working, input and then output. How is current state calculated? From the current input and the previous node's output. This is previous state, ht minus 1 previous state, ht input state, and xt is input state, ht is current state. So current state can be found from this. In RNN, it is quite simple. And tan H formula, weights and that. Okay, bidirectional. This is bidirectional LSTM. From forward direction as well as from backward direction, you are feeding. Here, this is forward LSTM. S naught, this X naught, X1, X2, and up to some value Xi. And here, look at here, this is backward direction. This is yi, y, and so on up to y2, y1, y0. When the LSTM system is at this place, it has both the previous input data elements and the succeeding the following data elements. Both are there at this place. How is new candidate calculated? In LSTM, we use activation values, and then we have two outputs, new activation and new candidate value. Candidate value is that only what I told you. Colleges near, if you just type colleges and if you get near, if you get offering, and having, these three words are the candidate words that can come with colleges. So here this new candidate word. What will be the new candidate? It is determined from the weight of previous state, current input, and bias, and you apply tannage on this. This is like, weight of this activation as well as weight for this x. You have that x multiplied with its weight, a multiplied with its weight, and that you sum, and then you add to by a bias unit, and then you take tannage. Update gate, forget gate, and output gate. In LSTM, memory cell has three different gates: update gate, forget gate, output gate. Here outputs will be, we have two outputs from LSTM. Why we have two outputs from LSTM? Because we are working with Bi-LSTM. Bi-LSTM will have two outputs. Okay, example here given. Okay, here some animation is shown. He said teddy bears are on sale. Because of these bears, this teddy is not a name of the person. And here, look at this Teddy Roosevelt. Because here you have Roosevelt after Teddy, it means that this Teddy is the name of a person. Teddy Roosevelt was a great president. Here, teddy bears are on sale. What follows? What is this Teddy? Is it a name of a person or name of that toy? That is determined from this following word, and that is possible through LSTM, Bi-LSTM. It is connecting forward as well as backward, like this. And both the activations, forward and backward, would be considered to calculate the output. Uh, this is Bi-LSTM. Okay, Bi-RNN we will look at tomorrow. Rachna,
Ma'am,
1 minute. I will stop recording and talk to you.